Basharul, how is your project? Where it has
So it's
reached?
going on, sir. Nowadays I'm scrapping, sir. I mean, I have to scrap a lot. So
Yeah.
yeah.
So, have you been able to develop a good set data set?
Uh, yes, sir. Some of the classes doesn't contain much data, so I'm just filling the gap. Like I'm thinking of grabbing 1,000 image per class. So there are around 13 class now. Like mask improperly weared and mask weared and types of mask. So I'm covering everything.
So, what percentage of work has been completed?
Like 40 percentage.
Okay.
Yeah,
You know
it's
the
still low,
deadline.
but I'm trying my best.
Okay, you know the deadline of submission, eh?
Yes, sir. January.
Okay, okay, okay. But you are confident that it will be completed.
Yes, sir. I am sure.
Hmm. Okay, good luck. And how situation of COVID in Sri Lanka?
The situation is getting worse now. I mean, like certain areas are under smart lockdown, and you may know that they are cremating the souls. So there are some issues too, like the minority is concerned and all. So we hope everything will be good.
Uh, what sort of issues for minority? I mean, how they are
Like
living
sir,
with COVID?
like sir, that they are saying that due to this COVID-19, when they are going to bury it, it may create some groundwater contamination. So they are saying the only solution is to cremate the souls. But you know that in Islam we cannot cremate. So many of the politicians are against it, and many of the minorities are not satisfied with this answer. So we are just, we are even many people have appealed, and still they are considering. I mean, now some of the virologists, they are saying that there might not be any contamination, and now some of the people are speaking even from the majority. So it's like a political scenario, but we are hoping they will get a good decision. So it will be good for all the people, like the majority and the minorities, because in Buddhism they don't need to bury the body, they cremate it.
Mhm.
So that's the things.
Right, right. And then, are you following LPL?
Yes, I think gladiators won too much now. So yeah, I mean it's not that much interesting like IPL,
Right,
but yeah, it's good.
right. I mean, at least it is Sri Lanka's own Premier League. Eh?
Yes, first time they are conducting, so there might be some problems,
Mhm.
but in future it will go for the heights.
And I think many TV channels are showing it live, so it seems like there is some interest worldwide. That is the reason why
Yes, yes.
channels have done some investment in telecasting LPL. And I think,
Actually, sir, the
yeah,
sports minister is the brother of no, the son of prime minister. You may know about the Rajapakshas. They are the one who is in the present governance. So, like the Gotabaya Rajapaksa is the brother of former President Mahinda Rajapaksa. So the Rajapakshas are ruling. So and Namal Rajapaksa, they have some investments here and there. So they can pull the strings from here and there. So they might do something good to the country.
oh,
So yeah,
good, 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 good. And otherwise, how's weather in Sri Lanka?
nowadays it's lovely. I mean, we have a lovely weather all the time. It's not that much hot. Like in Sakkar, you can see in March, it's hard to survive.
That's
But
right.
in here, it's nice. I mean, the weather is good.
Are all 12 months, what is the minimum temperature that goes in the year?
Yes, in our area, like 29 is the maximum. I mean, the maximum. The minimum will be around 9, 10 Celsius.
Okay, okay, okay. And
But it depends. If you go to Jaffna, the northern part of Sri Lanka, it's little hot. Like not like Sakar, but more like 47 Celsius, something like that.
right, right,
Yeah.
right. That's good. That's good.
Yes, sir.
What time is now in Sri Lanka?
So it's 6:21.
Okay, so 621. 621.
Yes, sir.
How come? It means you are 30 minutes
Uh, I think 30 minutes. What we
plus.
call
30 plus. Huh?
yeah, plus, yeah.
Okay.
It's 5:30 GMT in Sri Lanka. I think in Pakistan it's 5 GMT.
Yeah, that's right. That's right. And how many hours it takes from Karachi to Colombo?
Uh, 3 hours, sir.
3 hours. Wow.
Yeah,
Oh, that's not a lot. I mean, when we go
yeah,
to Islamabad from here, it takes around 2 hours. So it's a
yeah.
long flight.
Yes.
Saif is here. Others are still in mosque offering prayer.
They might be on canteen, sir.
Uh, you mean Irfan is also in IBA?
Yes, sir.
And Nimraj in IBA, and who else is in IBA?
Yes. Uh, I think other than these guys, no one.
Okay,
Khalid just went home.
okay, okay. Hmm.
So Hasib said he's facing load shedding issues, so he will watch the recorded lecture.
Okay, okay,
Yes.
okay. Hasib and Abdullah.
Uh, I'm not sure about others. Hasib just messaged me.
Uh,
Like, yeah.
okay, right. And Maureen, and yes, run away. In
Sir,
Spain.
Noreen might have class of NavTech. She's basically teaching big data in NavTech, so she might have a class.
Hmm.
Yeah, she has some issues. I mean, her class stops at 7:30 or something, so she couldn't join at Fridays.
Yeah,
Okay,
she's teaching in NavTech, sir, big data.
Yeah.
right. Irfan.
Irfan is here, sir.
सर
Irfan, you are 4 minutes late.
सर एक्चुअली डॉक्टर जावेद शाह नहीं मिली हुआ सर रास्ते में
मैंने तो बताया मुझे क्लास है.
अदब को ॿुधायो मांसि
तॾहिं त छॾियईं साईं.
Hmm. ऐं निम्रा पॉइंट टू टाइम क्या है इरफान?
सर पॉइंट हलंदी ई न आहे हाणे आई थिंक
निम्रा जी पॉइंट ते विझो.
पॉइंट
अच्छा
मथां हिक मथां हलंदी हुजे सर इवनिंग में मे बी.
हाँ.
थी सघे थो सर छो मां
हो एम्प्लॉइज़ जे लाइ साईं और जेके सिटी जा एम्प्लॉइज़ हूंदा आहिनि उन्हनि जे लाइ मथां हलंदी हुजे पॉइंट.
हा उन्हनि जी हलंदी आहे पर उहा त 4 PM ते न हिन टाइम थोरी
मे बी इवनिंग में का हुजे या हुननि जे लाइ जेके नेवटेक वारा स्टूडेंट्स आहिनि या 3D वारा
हा
आहिनि.
कैपटेक एग्जैक्टली उन
तव्हां
में
घर
3D वारा बि स्टूडेंट्स
तव्हां घर की
फिजिकली था पढ़नि न.
तव्हां घर कीअं इरफान?
सर मां
इरफान
बाइक ते
सखर जो
वेंदो
आहे
आहियां
साईं. इरफान
हा
सखर जो आहे.
त
इरफान
निबरा बि
टेंशन
सखर
न
जी
वठो.
आहे पीरगोट जी न आहे
इरफान है.
अच्छा 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 अच्छा.
हाँ पोकी में होता.
सर बाइक ते सर
अच्छा बात क्या है? ओके, ओके.
यस सर
Okay, so I think enough people have already joined. Ghafoor is here, Khalid is here, Saif is here, Irfan is here. So we can start. Sharing my screen. Okay. Uh, right. So I think you got the idea of how attention is actually paid, mathematically, and you know this is typically a neural machine translation. You will have at input, right? uh, this is an encoder. You will have context vector, and then during training you will provide, you know, input, also the predicted words. But when you are in test mode, you certainly will hide this just to see if prediction is being correctly made, right? Let's see neural machine translation, how it is implemented in Keras. I show you one example, and I'm hoping that you will be able to replicate it. Just 1 minute, I don't want to lose this recording. Okay, so E teaching, 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 E IBA, IBA, IBA. teaching. Okay, fall 2020, deep learning online classes. Okay, right. So, okay, okay. Zoom. This is neural machine translation part 1. I will upload it after class. Okay, so here we have neural machine translation. Remember the data sets that you will be using for this, they are actually, they look like this. If you have only this, you can have a neural machine translation data sets. We have yeah, come on, deep learning. So if you see data sets, uh, we have this from German to English, from English to German. See this data set. You just need a data set in this format, and luckily we have got many other possibilities available. So from English to German. So this is high in English and it's corresponding in German. High in English, another possibility. Run, and this is the German translation. Wow, German translation. Really, huh? Beat it, go away, hi Tom, wake up. There are, I think, more than 100,000 sequences available in English, and they are corresponding in German, and all of them are tab separated. So
Tab separated, right?
we have on left the English, and after tab we have the German. So we just need a data set in this format, and we have this data set format available in almost many languages, even in Urdu. Yes, there are no availability in Sindhi, but in Urdu this is available. So this data set is there. For Urdu, you can see even for Spanish is available. Also for Urdu, this data set is available. This is a bit noisy. You will have to remove a lot of noise from this data set in order to make it usable, and this will be one of your assignment. It's just a 30 minutes assignment. So end of the class, you will be doing it. So you can see he still has not responded to my letter. इसने अभी तक मेरे खत का जवाब नहीं दिया. So again, you can, this is a bit noisy as I told you earlier. Sentence, tab, and then another sentence, but also they have this type of additional, data which actually shows who have contributed. So you will have to clean this data and then use it in NMT, neural machine translation. But first, I will show you one example from English to German. Right. So the first step, you will load the document. We will load document. Encoding has to be UTF-8 because it will be using a lot of non-English words. Right. So we read this file and store in text, and then close the file, return the text. Simple Python. We convert, when we read the file, we convert it into pairs. So the first pair, we split them by tab. In the pair, first element will be the English, and second element will be its corresponding German. Right. So this is second method, the second function which converts document into pairs. The first method reads the document, then we clean it, remove all non-printable character. Sometimes there are emoticons and other things, we are removing them. Remove all the punctuation, normalize all Unicode characters to ASCII, normalize the case to lowercase, and remove any remaining tokens that are not alphabet. Right. So we do all this pre-processing. We have been doing it in almost every task. So for in each line, for every word, convert in lower, translate into table, where table is actually containing all those strings which are removable. Right. So we actually clean this text and return the lines which are cleaned, which are actually not having spaces, not having special character, and all of them are converted in lowercase. To pairs, clean pairs, okay, all these three again written. Now I'm going to mount my drive and read this file I have uploaded on my drive, right? deu.txt, which is actually from English to German. Loading the file, converting them to pair, cleaning them, right? And I save this cleaned version, right? I save this cleaned version here, NLP and English. So this cleaned version, which actually looks like this. Huh? So for each sentence in English, the corresponding German is written here, right? So this cleaned version, we are going to store uh, in my drive, right? Now, once if the data has been cleaned, the next step is uh, we are loading the cleaned version, right? We open all these sentences, raw data. I'm in this uh, cell, I'm doing nothing. I'm just preparing my test data and training data. So what we actually do, we use only 10,000 samples, right? So 9,000 we will be using for training and 1,000 will be using for test. So I have got this data set. I say from raw data set, which is actually my clean file, which I've just loaded. I say from 0 up to this point and both, I mean, English as well as German, right? So I load these and store in data set from 0 to number of elements, number of sentences. So 10,000 sentences. So this data set is actually containing 10,000 elements from my data set. I shuffle it as a good practice, right? Then train and test from data set 0 to 9,000 goes to train, and then 9,000 to 10,000 goes to test. I save it back on my drive. So I save English both, I mean train and test, then train and test, right? So they have been saved on my machine. And then, now this is my tokenizer. You know what we do with the tokenizer, right? uh, we just want to find out what is the size of maximum length we need it, because we want to estimate. If you see this, we need to see how many encoder we need and how many decoders we need. So we need to figure out what is the maximum size of one sentence in English and in German, right? So that is the reason why I actually get all the sentences and see which one is the biggest sentence, the sentence with the highest number of words, right? So we get that maximum length. You can see here length line that is split for line dot line. So we will get length for all the lines, and we return the one which is having maximum number of words, right? Now once if this is done, I say create tokenizer, this one, right? Create tokenizer on data set, you mean all taste and trend. Then English vocabulary size, I get by using, by seeing the length of English tokenizer, this one, right? I mean all unique words, all unique words. Similarly, I get the length of my data set, right? So we print English vocabulary and we print the maximum length. So you can see the unique words in English are 2400 plus, and the biggest sentence is having 5 words. In German, and the number of unique words are 3800, and the one which is having highest length is 10, right? The sequence which is having highest length is 10. We get it because of this code segment, which is nothing, just repetition of this on the German part, on the German part of the data set, right? Now once if this is done, we do encoding of the I mean the converting them in the encoding, right? So we say encode sequence, tokenizer text to sequence. We know why we do it, and we paired sequence. We make all sequence of the same size, right? We also encode output. Your output is actually the German vocab. So we will be encoding the output as well, right? So here I prepare input for my encoder. So encode sequences. We are passing, German tokenizer. and the length of German words, right? And we send all. And this is train X and this is train Y, right? So we actually encode sequence again on the English train X and train Y, train X and train Y. Train X is German and train Y is English. Then train Y, I'm doing nothing, just encoding it. This is to encode sequence and this is to encode complete Y, right? And then this is whole for training, and same I repeat for the test, the validation, right? Then we create the model. You can see here, when I create model, I say define model, I'm calling this method. I'm passing German vocab, English vocab, length of German and length of English, right? When I pass all these three, I create a sequential model. I create an embedding layer. In the embedding layer, I say its dimension should be, source vocab, what I'm getting from here. Number of units is 256, right? Input length is equal to source time stem, which is actually as German length, right? And then mask 0 equal to true. I add another LSTM of 256, right? Uh, a repeat vector is actually to send, to aid the decoder side of this, NMT, neural machine translation. There I add another layer of LSTM, and then finally the output of this, which is time distributed, a dense layer. The output is, target vocab, and the activation that I'm using is softmax. Now remember, how, how much is the output of this whole model? The output of the model is number of words that I have in target language. My target language is German, so the number of words that I have, they are actually output of my model. I mean, you can see here. If this is German language, the number of output that I should have here will actually be the vocab size that I have in my target language, right? And activation has to be softmax because it is not binary. So at one time we will be predicting one word, so the word which is having the highest probability, right? So we prepare the model, we see model summary. You can see this is the whole model summary. You can also display it, right? uh, we can save it, and then finally we fit the model. When you fit the model, you provide training X. Remember, this is English. Training Y. Remember, this is German, right? 30 epochs, batch size, and for the validation we pass test X and test Y, right? So you can see here, it actually starts its training. When it starts its training, with every passing stage, you can see validation loss is reducing. Once if the model is trained, it does not take a lot of time. It just takes 5 to 10 minutes. Right. Now let's evaluate the model. Now, once if the model has been trained, once if the whole natural language model has been trained, the next step we are going to do is to evaluate it. Right. For evaluation, we will do all these steps. Right. Loading, cleaning, creating tokenizer, maximum length, encoding sequences. Right. uh, all these things you have already seen. Here is the evaluate model method. What this actually is doing, maybe I should start from here. So I load the data set, train, test, English tokenizer, right? This time I will not be fitting the model. I'll just be evaluating. I will evaluate a model on both training data as well as test data. On the training data, I will be providing same sentences on which model has been trained. So logically, let's say performance should be reasonable on the sentence which it has already been trained upon. And then I will also evaluate model on the sentences which it has not seen previously. The test sentences, right? So here, English tokenizer, vocab, all these we have already seen. And in training, what I'm saying, evaluate model. I'm passing the model which I have trained, right? I'm passing English tokenizer, and then I pass train X and train, right? The train X is actually I'm getting the German X and Y, right? So I pause and see how model is performing here. So you can see here when you do this, the source is when source is this, right? The target is it should produce this, but it predicts this, right? So you can see here when we gave this at the source, this should be target, this should be predicted, but it actually predicted this one. I hate people. I know people, but it says I hate people. I'm often here. I am often here, and it predicts I am often now. The target is I'm escaping. Escaping. That's correct. Tom did not win. Tom did not win. Shall we dance? Shall we dance? Tom adores me. Tom adores me. You can see many of them have been correctly trained, correctly predicted. The reason is we are passing the trainings, the training data, right? The second is performance on test. Don't worry about this blue score. I will cover this next week. Still, there are some mathematics that I need to cover. We will see this blue and other, because you need to understand that security accuracy is not the matrix that we can use here. Accuracy, we say if the model prediction is correct or incorrect. I mean, when we have got class labels which are very discrete, I mean only few, but here in this case, I mean the translation which it has done is actually a sentence, is not the class label. So obviously accuracy cannot work in neural machine translation. So we needed better metrics to assess the performance of model. So for that reason, they actually came up with multiple metrics, and one of them is blue. There are many others. We will see them in my next week's class. Right. On the test data set, see its performance. The target was, did Tom hurt you? Did Tom hurt you? I mean, believe me, this model has not seen in past, but it predicts, right? This should be the actual, and it has correctly predicted. Pandas are cute. Pandas are cute. Go ahead, keep writing. Yeah, I mean this one is not correctly predicted, but many of them are correctly predicted. I am talking. I am speaking. Wow, I don't think this is wrong. Uh, I made a list. I made a home. Huh? I was devastated. I was be here. Huh? Do kids like you? Do me CC? Huh? I mean, some of them are not very, reasonable, but many of them are. Stay cool. Huh? Keep careful. I cannot hear you. I cannot hear you. Huh? I'm busy here. I'm busy now. So you can see many of them are correctly predicted. But remember, this was only on 9,000 sentences. If you train the model on all the German to Urdu, you will I mean English to German, you will probably see better accuracy. Right. So the whole thing is you just need to have a data set in this format, the one that I've showed you. Once if you have that, you just need the data set in this format, and once if you have, you can train your neural machine translation LSTM. Remember, the only difference from typical classification task is the number of output is actually equal to number of all unique words in target language. Number of all unique words in target language. And input is number of unique words in your source language. And then obviously the input and output, when it has been defined, then you need to define uh, the sequence at each stage. And when you define sequence at each stage, you actually see what is the length of maximum sequence, and you pair those sequences which are smaller than maximum, and you will not terminate because we do not want to lose the information. Right. So these three or four basic things that you do, and then you use LSTM in this format, your model is ready to do the prediction, to do the translation. And we have seen in this example, its translation is reasonably well. Right. So what I want you guys to do, I want when this class ends, when I complete Transformer, I will be uh, giving you, um, I will be giving you Urdu text. I think it's available here. It is available neural machine translation. Now, neural machine translation, neural machine translation. It is available on some website, which I am unable to recall now. I think it should be where it should be. I forgot it. The website name I remember, but now I've forgotten. So you need to download it from there, but I'll keep it on our LMS. This will be available on LMS, and I will also make this available on our LMS. But these all are available on one website. Many things. I think the website is many things. Many things are what? There was some strange name. Uh, mm, many things, many things, sentences, many things, org words, English sentences focusing on, I think this was the website. uh, Many things, many things, many things, data sets, data set, English, Urdu. I think English Urdu sentences from many things.org. Yeah, it is many things.org. It should be available here. It should be. You just Google it, you will get it. But I think here they are unprocessed, but at some other, page they have kept processed. Uh, some other page they have kept in a very, you know, processed form. I will share with you the link, but I will also keep all these available on LMS, and I want you guys to use this data set from Urdu to English, and code is already there. The only thing that you need to do is to clean this and then use it the way that code is using. So uh, I will upload this script, and I will upload this Urdu to English translation, and I want you guys to give me Urdu to English translation. Clear? It should be a 30 minutes assignment, and it should be interesting assignment. Will you be able to do it?
Yes, sir.
Inshallah, sir.
Inshallah, sir. Nimrat here, inshallah. Okay, good, 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 good. Kainat, will you be able to do it?
Inshallah, sir.
Okay, good, good. I just wanted to confirm you are also there. I'm happy that you are still with us. I mean,
Yeah, sir.
it's not easy to not have attraction of grade and still participating in the class. Okay, so any question up to this point?
Sir,
Yes, yes, Irfan.
sir, you said accuracy in this case may not work, but you see, in the whole data set, we have these sentences and their corresponding translation. So by counting the correctly predicted and actual, we can measure the accuracy. This is what actually the accuracy do.
Uh, you
I mean, we don't have a label, but we can count the number of instances correctly, translated, because
see.
we have a target.
Yes, yes, that's a very good question. See here, I am busy here. I am busy now. Now, what will you say? Is this correctly translated or not?
No.
No, I'll say yes. I'm saying yes. Because I am and I am busy and busy. So there is no correct translation. There is no incorrect translation. There are many partially correct. So you need to give credit to those as well. So you need to understand that the target was to predict I am busy. So it has predicted I am busy. Only one word is incorrect, which is now. What Bilu and Raj, all these metrics do, they actually consider these partially corrected sequences. So that is the reason why we say accuracy is not a good metrics to estimate performance of neural machine translation. So that is the reason why we have got these new metrics available to assess accuracy of, to assess performance of neural machine translator. Right. I will cover these in detail in next week because I've got one full lecture to just understand all these metrics that we will be using in transformer and neural machine translation. Clear?
Yes, sir.
I'm very excited to see if you people can implement it. And then believe me, it's a very easy assignment, just 30 to 40 minutes assignment. So I will upload everything, and I'm expecting that before weekend, you should be able to, implement it. Okay, so the neural machine translation with, remember this is not implementing attention. This is simple LSTM. We are not doing any attention thing here. Huh? The attention thing we will do in our next example. Before that, let us now understand this beautiful concept of transformers. They actually change the way we work with text data, not only in neural machine translation, but also in classification, in chatbots. I mean, almost everything that you do with the text, transformer have actually changed it. They are behind the latest development in NLP, such as Google's BERT. I mean, BERT and GPT. BERT is from Google and GPT is from OpenAI. Now, both of these guys are kind of competing in NLP, deep learning. But to be very honest, both of them are using transformer. Both of them are using attention. The only difference is BERT is using transformer in one way and GPT-2 is using in another way. And other day, both these are based on transformer. So if you understand transformer, the understanding of BERT and GPT should not be a rocket science. So you will see that both of them are actually using transformer and attention mechanism. They are very excellent at language modeling, sequence to sequence modeling, and they are an engine for BERT. Right. Remember, NLP is in golden era. You need to understand that this is ImageNet movement in NLP. When we say ImageNet movement in NLP, you need to understand that we were doing computer vision differently before deep learning, but when we came up with CNN and when we solved ImageNet, we increased its accuracy from 73% to 96%. There was a moment when we all started feeling confident that now your machine should be able to recognize what is inside the image, with whether there's cat or dog or mouse or printer or laptop. We actually made a lot of sense of image contents because of that ImageNet movement, because of that CNN, right? So they say that in NLP that movement came when we introduced transformer. So such is the significance of transformer in NLP, because transformer is engine for both BERT as well as GPT-2. They are good at sequence to sequence model. Neural net that transform one sequence to another. I mean, this is the reason they are called transformer. When you read transformer first time, you think about Babda. Transformer has been burned, so 3 days load shedding. But this is not that transformer. This is the transformer which actually transforms one sequence into another, and that sequence can be from one language to another language, or it can be question mapping to answer, or it can be even one DNA sequence to another DNA sequence, or it can be one music sequence to another music sequence. So wherever you see sequence to sequence translation, a transformer is the go-to solution. Right, it consists of encoder and decoder. But remember, I mean, Transformer said one more thing. Transformer said, come on, why you are using LSTM, why you are using RNA. You just need, attention and nothing else. They even took LSTM out of equation. When we first saw attention introduction, at that stage we thought LSTM are here to stay, because even attention is using, LSTM, RNN, and GRU as encoder and decoder. But at later stage, when we came with the transformer concept, we say we don't need LSTM, we don't need RNN. All you need is attention, nothing else. I mean, the paper title was "Attention is all you need." So they said even LSTM and RNN, you need to take them out of the equation just to speed up the processing, and more importantly, because they are redundant. They say that whatever LSTM and RNN and GRU is doing, same thing we can do without them. So why we are adding complexity? So that is the reason why Transformer said, let us take LSTM out of equation. Right. Their working mechanism, I mean, you can just imagine that when they transform one sequence to other, they bring an intermediate sequence. And that intermediate sequence is understandable by source as well as by destination, by the target. Right. So you can consider transformer as a translator, a guy who understands both English as well as Chinese. So if he understands both English and Chinese, he's a kind of translator, a kind of intermediate guy. So he is kind of getting information from source and sending that information to the target. Right. So first language and an imaginary language analogy is what your encoder and decoders are doing. Right. So the attention mechanism looks at an input sequence and decide at each step which other parts of the sequence is important. You have already seen how it does it. You have seen this image. I have already discussed it. Right. So again, more or less the format is same. I mean the block diagram is still same. Neural machine translation has always been there, so it is still using same mechanism. It says that you will have a source sequence, it will do something, and then you will have, this will be called encoder, and you have decoder, that at the training time it will get input also at the decoder side, but when you are in the test time, this input will not be used, you will only be doing the prediction from here. So you see input and do prediction here. But when you're training, you send this and you have this input, which is the actual label, and then you get the output. So still the structure is same. Right. I mean, why these guys said you take LSTM out? They said it is because LSTM has got this vanishing gradient problem. They said, you said you can eliminate disadvantage of RNA with LSTM if you are sending the information in parallel. I mean, if you see this, if you see LSTM, if you see LSTM, we said something like this. Not here. This one. We said this is the CNN, RNN. This is RNN, and this is LSTM. Right. What LSTM is doing, LSTM says along with the hidden state, you also send this carry information, this carry track, this carry information. Right. So they said even when you reach here, you still have access to the remote past information. So you can have a kind of parallel build which is running, and every time if you want to refer to additional information, you can refer to this carry build, you can refer to this carry track, you can get that information from there. But Transformer said you can do it only probably for a couple of sentences, for 2 or 3 sentences. when you reach too far, this carry track would have been overwritten, because if you see its equation, this carry track is actually IT into KT into C plus CT into FT. What is IT? IT is actually current state and initially a random matrix plus input and initially a random matrix. What is FT? FT is current state, another random matrix initially, plus dot input another random matrix, right? And then you also calculate KT by current state and UK another random matrix plus dot with input and another random matrix, right? So you say that you calculate CT and it's a kind of parallel information which goes, I mean, it kind of gives, you know, it kind of always is available for all the steps of, LSTM. But we say when this becomes too far in past, it has been overwritten many times. So probably, if you have got a sentence like this, if you have got a sentence like this, here the word view is referring to the series of 11 images. So they said, would you be able to connect this with this? Probably not, because LSTM by nature, the additional information that it carries at each step, it is being overwritten. So you say that when you reach here, this carry is not only having information of this, but also information from here. And then when you reach here, this carry does not have only information of this state, but also from here, and also from here, and probably also from here, and maybe a remote past. But the problem is every time it is being overwritten. Every time it is being overwritten. Now, because it is being overwritten every time, so the information that it might have seen 10 sentences back, it might have forgotten. And that we do not want. Because sometimes the words which are referring, you call them possessive noun. Huh? These are actually the words which are representing to noun in the paragraph. So these sometimes are too far from their actual noun. So you can see here the series of 11 images that together create a seamless 360-degree view shows a city that was mostly destroyed in the 1960 earthquake. You will see railroad barons, wedding cake, mansion in California Hill, now Nob Hill, and dense development of brick and stone building mixed with wooden structure growing along the view. Now, the view is referring to these 11 images. It's too far. I mean, we humans have got fantastic ability that when I read the view, I know that the view is referring to this noun. But when you are in LSTM, when this was the word, then this was the word, when this was the word, when it reached here, it has significantly overwritten, this carry information. Now, this carry track may not be, well representing the information that we saw here. So we can say the problem that we had in RNN, that, you are not passing this carry information. If you see in RNN, you just have current input, right? I mean, current input and previous state. Current input and previous state. No carry information. But here, when we had this carry information, to some extent, we solved the problem of vanishing gradient, where we actually lose information of remote past, but still that problem is there. Because when sentences are like these, when the referral is quite distant from each other, then even this carry information is unable to, make a connection between view and the series of 11 images. So they said remove LSTM, because the problem due to which LSTM came in, they said RNN had a problem, but we have solved. They say, no, 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 no. They have solved, but to a larger window. But that problem is still there. And how about when window becomes too large? Even LSTM will not be able to solve that issue. So they said, remove RNN, remove LSTM, remove GRU, only attention. So they actually came up with an alternate idea. We'll see how encoder is now designed, because if you take LSTM out, you need something for encoder, right? But the thing is, they said you just need attention mechanism and everything else you can just eliminate, right? So the whole idea is to just strengthen our ability to refer remote past. We just want that we should be able to establish a connection between word view and the series of 11 images, right? So here, what they say, wow, I mean, what a concept. See here, they say for each word, you establish attention with all other words in the document. Say, for example, we say view might be sending attention to the series of 11 images, or to city, or to seamless, or to 360 degree, or to distance, or to brick. We say, let's test all possibilities. Let's check what view is referring to. Earlier, obviously, we don't know what it is referring to. So we say, do brute force. When I say do brute force, I mean just check view against all other words. When you have random weights, maybe the strongest relationship between view and brick is observed. Your training data will tell you this is wrong. Do the back propagation. Update weights matrix. Next time, the strongest relationship the network might tell you between view and seamless. You have training data. You say, no, that's incorrect. Go back and update your weights so that you can, refer to series until you reach here. Again, the back propagation is at our disposal, is at our rescue, right? So if you see this, this one is typical LSTM. We have seen uh, input, previous state, which is initially 0, and then output. This previous state is being sent to next step with the input. You get HT and then HT plus 1 and so on, right? You have seen this formula. We say HT is equal to, it is function of X and HT minus 1. I mean, we have already seen this. X is equal to HT minus 1. We have already seen this example. So we also saw this example. So we know that HT equal to any function, any function. Here we say 10H, but it can be ReLU or any other function, right? So it is function between HT minus 1 and X3. So it's a function between HT minus 1 and X. Attention says, okay, previous state, but also function between current input and previous state, right? Attention between current input and previous state. It is just like, this equation is representing this one. This equation is representing this phenomena. So this says, it is current input and previous all states, right? So output is not only dependent on current hidden state, but current input and all these hidden states, right? So attention equation is actually the simple equation. So HT equal to function of not only this input, but this input and all other hidden states, right? Which are actually coming from the encoder side. and this one is the decoder hidden state, right? So is you have already seen this equation, the softmax of all these states, which are actually 10h between ht minus 1 and x, right? uh, they also introduce another very beautiful idea. They said you want to establish connection between words, you need three beautiful concepts: query, key, and value. This concept has been taken from, I think, computer vision, maybe video processing. When you talk about YouTube, you actually write a query, right? Against that query you get some keys, right? And against those keys you've got the value is actual image. So say for example, if I am on YouTube, so if you are on YouTube, if say for example if you are on YouTube, you write any query, I say Pakistan versus uh, India, right? Now this is query, this is query. Now, what is after query? What comes after query? It is the key. Now, what is the key for YouTube? The key for YouTube is actually it is matching this with these titles. The title for this video, the title for this video, the title for this video, right? So it will be kind of matching my query with all these keys, and these keys are not only title of these videos, but this is also the comments which are on this video. When you are on YouTube, uses a lot of textual information, and that textual information is not only label of the video, but that is also the comments which are on that video just establish a link. So this is the query. The key is this, and value is this actual video. Value is this actual video, right? So query, key, and value, the concept that we have been using in video indexing, they say you can use it in transformer, right? So here if I say query is running, right, the key is girl and the value is actually this actual image, right? Similarly, if I say where is ticket, so you can see this actual image will be value for that, right? So here, I mean, even these type of relationships, which we have a lot of difficulty when we were in LSTM or in RNN to deal with. I mean, just imagine how childish we were to have these pre-trained, word embedding. We said we will give you GitHub, and GitHub said I will give you embedding for each word, and that will be very unique. And they also said the embeddings will establish these type of relationship. I mean, they were right on that. If you see, the whole initial effort, it was we wanted word embedding, and we wanted that word embedding should have the relationships like they should have the relationships like, come on, why my machine is so slow. Okay, so they said we want to have these type of relationship, so if I have king equal to queen minus uh, lady, or maybe female plus male, right? So we said that these type of relationship should exist, so if say for example the embedding for king is 0.90, we said if queen is 0.7 or maybe 0.4 or maybe 0.95, right, then female should have maybe 0.07, right, and then there should be 0.02, right? So we said this type of relationship should exist. If you are giving me word embedding, then give me for king 0.90, for queen 0.95, for female 0.07, for male 0.02. Why? Because I know that in practice, king equal to queen minus female plus male. If you take out female from queen, royalty is still there. Royalty is still there. She will still be royal. And if you add male in it, it will actually be a king. It will actually be a king. Right. So they said maybe if you have got a maybe point 0.5 for boy, then for girl it should be probably minus 0.5, the opposite of it. So those words which are opposite to each other, they should have opposite numbers representing to those values. So we said we need word embedding, and we thought that word embedding is the solution in natural language processing. And when we saw glove and when we saw fast text, they were really doing this job. I mean, when you plot queen, king, all these things on, some 2D plot, and you saw that really good, excellent, pretty, they were close, and good and bad were very far from each other. Because good, excellent, they were used in same context, and bad was being used in different contexts. That is the reason why when you plotted these words uh, as per their vector from verb to wake or from glove or from fast text, we saw that these relationships are existing. So we thought we have solved the problem. But then this was the problem. If you drive down the road and follow the river bank, you should find the Bank of America on your right. This is the problem. The problem is, oh my God. Word to vector will tell me what is number for bank. And that will be same for this bank as well as this bank. And we'll be committing a mistake. Because this bank is the money bank and this bank is the river bank. So here, bank is not same. Bank is not same. So obviously, word to wake or glove or these type of childish type of embedding techniques, they are not solving these problems. Transformer said, I can do the solution. They said, if you want to do translation, if you want to do next word prediction, if you want question answering, I will tell you how to do that. They said, when you are here, you want that what should be next word, then you will have to attend all other words. You have to pay attention to all other words. And if you can provide me proper training data, I will update my weights so that Riverbank and Bank of America, I'll be considering differently. Bank will not be having only one embedding. Bank will have as many embedding as there are words in the data set, right? And what will be those embedding? Those will be learned from the data, right? We'll see a couple of example and then it will make more sense. So here again, this is the general diagram of a transformer, which seems pretty same as we have been seeing in neural machine translation. We have on the encoder side, all the sequences we train. We have context vector, and from the context vector we can decode. Right? They say in transformer, each of your word is query. Each of your word is query. Right? And all other words are actually key. And the value is the word which is most important to that query. Right? So if is Q1, U is Q2, drive is Q3, and so on. Right? So say for example, when you've got Q4, probably right, bank, river, road, down, drive. These are the few words you attend upon. Some of the words may not be attended very strongly, but other words are being attended more strongly. So when you are here, the river bank, when you reach to bank, you need to attend river as well as bank as well as follow, all the words which are important for query bank. And when the query 16 is bank, you again need to focus on all other words. And when you focus on its right and its left, you saw that there is America. which means that this is different bank. This is different bank, right? So with this just one simple concept of query, key and value, we are able to make sense of which words we need to focus upon when we, when this bank is occurring, all other words are keys. All other words are keys, right? But which word we need to be focusing more upon, it depends on our training data, right? So in this case, it says that when query 16 is there, you need to pay attention on word of, on word America, on word find, right? Probably it says you can ignore that because that is a very frequent word. And this type of attention matrix, which word should be attended more, which word should be given more attention, these will be learned from data. Because when you are training, you are not only encoding your English, but you are also at the decoder time providing your English. So decoder knows that if this is the context vector, I need to produce this word. If this is the context vector, I need to produce this word. So at that time, we have this available at the input. But when you are testing, you are actually hiding this input because you do not have it available. Huh? I mean, if you are actually testing your model at that time, you do not have the the corresponding target value available. You need to predict. You need to predict from here, from the context vector. Right. So not only the transformer said remove LSTM, but they also said do it parallel, do multi-head attention. Now let's see it step by step. In any transformer, by the way, this one is the whole diagram of transformer. I want to show you. This one is whole diagram of transformer. Only then you will be able to make sense of it. The transformer, the multiple encoders and decoders, multiple encoders. So this is whole transformer. In transformer, encoder, 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 encoder. Output of each encoder is being sent to each decoder. Right. So even from here, you can see the input is to the each next encoder. The output of last encoder is going to all encoders, all decoders at the decoder side. Right. Now, each encoder, what is each encoder? This is each encoder. In each encoder, we have at attention layer, we have query, key, and value. Now, how attention is calculated? Remember, we do not have LSTM, right? So we need an alternate to LSTM. We'll see what is alternative to LSTM. But to this attention layer, we are sending Q, key, and V, right? We'll see how Q, K, and V is estimated. Then we concatenate them. We do layer normalization. We have a feed forward layer, a ReLU, another feed forward layer, concatenation, layer normalization, and then the output. Right. Let's see how all these are estimated. So basically, to each attention layer, the thing that we are sending, these are actually 512 dimension words. And these words, it is important to understand. You need to understand this, because when you will have words, you cannot send them directly to attention layer. You need embedding. So here, transformer says you can use any embedding. It says you can use TF-IDF, term frequency and inverse Jackman frequency. You can use it here. If you want word to bake, if you want, the glove, it says you can use any. It's up to you. But whatever you give me here, I will be updating it, right? If you remember, when we were using glove with LSTM, we said first layer should not be trained, because if you update the weights of first layer, your embedding layer, you are actually disturbing glove learning. So here, the transformer says you can give me any embedding, but remember I will be updating it, right? I will be updating it according to my needs. So here you can use anything, TF, IDF, glove, word to make, whatever. But each word need to have an embedding that you understand, because we cannot directly give word to the deep neural network. We need to give an embedding. So that can be any embedding, right? So we convert all these words into word embedding. They go here, and then we have got encoder, which gives us an output. Let's see what encoder actually does. See here, this is what encoder is doing. Very simple. Wow, very simple concept. Eh? It says for each query, key and value, I will do softmax. Attention is doing nothing. Just softmax on query, key, and the transpose of key, and divided by root of dimension. The dimension is 512, so the root of this. So if the dimension is 64, so you will divide it by 8. If the dimension is 512, you will divide it by the root of 512, and then to this whole multiply b. Why we are doing it? I mean, this division we are doing just to ensure that number is not too long. If it becomes too long, it will be difficult to manage. So it's just a small trick just to keep it at manageable level, right? So we actually multiply query with key, divide it by dimension, and multiply it by v. Now the beauty is, your query is the word that you are currently playing with. Your key is all other words, right? And your value is what you should actually be focusing upon. So initially you might say that when there is bank, I will focus on it. But when you saw wrong output, you know that you will have to update the weights so that bank is not referring to it. Bank should be referring to America. So you will update your weights accordingly, right? So the only thing that it is doing is this simple calculation: Q into K divided by dimension and the value, right? See here, I mean, this will make more sense, the simple example. So say for example, if these I have written all these steps, I have written all these steps, I have written all these steps. Step, yeah, first step. So first step is, say for example, I have got this at the input, thinking machine, right? So embedding for thinking x1, embedding for machine x2, right? What is query 1 and what is query 2? Uh, these are nothing, just random values, right? They are being multiplied with this random matrix, right? So we generate a random matrix WQ. This WQ is being multiplied with Q1 as well as Q2. Now Q1 and Q2 we have actually driven from X1 into WQ and X2 into WQ. So we actually got Q1 and Q2 from this and this, right? And then we have got key 1 and key 2. They are also being generated from WK and then input, and then value another random matrix, and we are producing V1 and V2, right? So these three, query, key, and value, they are nothing but initially they are these random matrices, right? And we update them as we move along, right? So see here, this whole step. So when input was thinking, so here is the encoding for input, right? The thinking, and this is encoding for for machine. Remember, it is not LSTM. When we had LSTM, we are taking one word at a time. But now, because it is not LSTM, so we have focus on all words. So we have complete view of the document. So if in the document we have got two words, so we are focusing on both words. So x1 as well as x2. But for the time being, okay, let's wait for Azan. I think this is one way Saif actually gave me an indication. Just a moment. We wait for the Adhan.
सर आजान खत्म हो गई है.
Okay, okay. Okay. So this is the word. We get embedding of the word, and where the embedding will come from, You can use word to big, you can use glove or whatever, right? And we get embedding for both machine as well as for thinking. Then we calculate query, where the query is coming from, it's a random matrix multiplied with x1, then key random matrix multiplied by the x1, and then value, right? Then we calculate a score for thinking. Remember, here we are actually estimating attention for thinking. We want to see, when we are focusing on thinking, what other words we should be attending to, what other words we should pay attention to. So we say q1 into k1 equal to 112, and q1 into k2 is 96, say for example. So we actually have just one quantity, which is suggesting that when you are having word thinking, focus on thinking. And this is another quantity which says when you have got word thinking, focus on machine, because this is q1 and k2, whereas k2 is actually driven from machines and k1 is driven from thinking, right? So this quantity, this is score, is actually telling you that which word you should be attending to. In third and fourth step, what we do, once if this score has been calculated, uh, q1 and k1 has been done, we divide it by, in this case, 8, because the dimension is 64, right? So this is 14, this is 12. We soft max them, right? When we soft max them, we actually then concatenate them, huh? uh, this v1 with v2 with all other v's, we actually estimate z1, which is the output for this stage from the word thinking, right? So when we gave x, right, we multiply with wq to get q, then key, and then v, and we do it for all other words in the document, right? So overall, with this simple formula, and when you actually see here, when you've got this thinking machine, attention 0, when it is thinking, we say we will get one attention, and attention 2 will get another attention 3, all other words that we have in the document. So for each attention, we will have nothing but z0, z1, up to whatever words you have in the document, right? So there are 2 to 3 advantage to that. It says when you got Z0, which actually says focus on word itself. Z1 says focus on word 1. Z2 says focus on word 2. Now when at the training time, when we see that the attention which has been calculated for word 1 is incorrect, we have these matrices to update. We have these matrices to update because initially they are random. Initially they are random. So when we update them slowly, gradually, things will be like these. Things will be like these. The animal did not, I mean, when you see this sentence, the animal did not cross the street because it was too tired. Huh? If, say, for example, this is the sentence, and here I want to see what it is referring to. Because here, if you see, even as a human, we sometimes confuse. The animal did not cross the street because it was too tired. Huh? Now the question is, who is tired? Is it animal or a street? Huh? If I write here now narrow, now what it is referring to? You will say to street. But
Street.
now if I say tired, what it is referring to? In this case, probably animal. Because street cannot be tired, animal can be. A street can be narrow, animal cannot be. So, here it may refer to any one of these two, noun, but which actually it depends on the context. So, transformer says you will have to estimate attention for it to all other words, to all other words. So you can see after certain training, after updating theory, key and value metrics, you will establish this type of relationship. You can see here it, the strong some dark color, it is referring to the, it is referring to animal, it is referring to didn't, it is referring to underscore t or cross the street because it even it is referring to itself, but that attention is very weak, right? So you can see transformer tells you which other words you should be attending when you are focusing on this word, which other words you should be focusing. And this relationship that it should be referring to animal will be established by updating this query key and value vectors, and we are able to do it because we've got a lot of data, right? So from self attention we get all these attentions: attention for thinking, attention for machine. The good thing is, probably the best thing that transformer did, it actually brought a parallel structure. They said, these all are independent. So you can, you know, learn their weights independently on a distributed network, right? I mean, they are not necessarily to be running at same machine because they can parallelly learn their attention vector, and learning attention vector can take place in parallel, which means that multiple machines can also be attending to the same task, right? Once it is done, then we have got feed forward neural network, and that is the end of the encoder, right? So every time we are doing nothing, we are just counting or maybe estimating attention for each word, and attention for each word is nothing but yet another vector, and that vector is actually this z, right? So for thinking, attention to thinking; for thinking, attention to machine. If there is another word, then attention for that word as well. As you saw in this simple example, simple example. So here, in this case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 words in this sentence. So we actually estimated attention of all other words to it, including it. And you can see that relationship is very weak. And it is because we have trained the model on a lot of data. And these WQ, WK, and WV have been, very properly updated. Their weights are now updated. LSU eliminated. Only softmax, only query, key, and value concept. You get a Z, which is attention for one word against all other words. And what you should be attending to, that will learn from the data. Right. Finally, I mean, it is just like this. For each word, you will have all these matrices. For K, for Q, they will give you, Z, and Z's are being sent to the decoder. And then decoder should be able to, do this. Right. I end it here. Uh, I'm expecting that you guys will be doing English to Urdu translation with NMT, with simple NMT. The transformer implementation we will see in the next class. Any question up to this point? Any question? Any question?
No, sir. We will
Sir?
study in detail, and in next lecture, inshallah, we will ask you the more questions.
Okay, okay,
First, we will have to study in detail, sir.
okay, okay. Does it excite you?
Yes, said that.
Yeah, sir, definitely.
Because
Yes,
I
sir.
mean,
But sir, I think it's very costly.
uh,
Costly.
it does.
Costly
It does.
in terms of processing.
Yeah,
Sir?
that's for sure. That's for sure. Nimra?
Uh, i- if we compare that.
Sir, please upload this recording because sir, I missed some points because of some reasons. So please upload this recording.
I will do that. I will do that.
Thank you, sir.
By the way, I'm uploading this English to Urdu data set. You will have to do the NMT, neural machine translation, from Urdu to English. Right. So this data set is now available there.
Sir, please also upload the script
The script I have taken.
for German to
Okay.
English,
Okay.
which you just.
So is there any data set available for English to Tamil?
uh, sorry.
Is there any data set available for English to Tamil? I mean,
Download this. I'm keeping it IBA teaching fall deep learning data sets नई lectures के अंदर NMT ठीक है. So I'm going to upload this as well. Okay, 8 English to German script Python. Right. Okay. Okay. So this has been uploaded, right? And now I'm hopeful that you should be able to uh, do English to Urdu translation. Do it before weekend. I'm not saying it's a graded assignment, but I'm saying it is mandatory. You all have to do
so,
it.
so shall I do it in English to Tamil? Maybe I will find a data set and do because I might not understand the Urdu letters.
You can do it. Yes, yes, you can
Okay,
do
sir.
it.
Okay, okay. So thank you.
Mm. Okay. I'm going to end lecture from here. You can all leave. I will upload this recording. Okay, thank you. Thank you all. I look forward to your solution for Urdu to English or Tamil to English.
Okay, sir. Thank you.
Bye-bye.
Thank you.
Bye-bye. Thank you. Thank you all.
Allah Hafiz, sir.
Allah Hafiz, sir.
Allah Hafiz, sir.